First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts who are not experts this week. Experts, Roy and Whisker. Hi, guys.
Constant abuse on this show sometimes.
No. It is
All the
merely
blood, sweat, and tears we
truth.
put into making you not an expert on so many other topics, and as soon as you have done more research on something than we've had time to do,
It is
you want
merely
to attack
truth.
us and beat us with it.
Maybe. Sigma Delta Modulation.
Oh, we're back to that again.
Actually, yes, well, kind of. But I actually wanted to mention that I have started trying, yesterday, I tried to program in C. I, Googled one of those like C tutorials just to see, no pun intended, like how I could, whether or not, now that I've had a little experience in spin, whether or not I can work with it, and
So what's the verdict?
I'm really glad I started in spin before C.
Why is that?
Because C is ridiculous. There's like
not ridiculous.
There's like brackets and pound signs and like semicolons all over the freaking place, like a and like I don't know. It just I think if I had seen that first, coming new into programming, I would have run away like crying.
So a lot of the same problems are solved in spin. They're just solved in a slightly different way.
Well, indentation and
new lines and indentation
Right.
are very important in
Correct.
spin.
Correct.
And not
Which
so
makes it
much
neat.
in C because you're using characters to represent those same breakpoints.
Right.
That's a really bad word for them, but yeah, those same. The compiler needs to be able to find what's what,
Right.
Has
one
to
way
do
or
with,
another.
with scope is usually the designator there.
Scope?
Changing scope. So like when you do an if, and then what you wanted to do if the condition, say if condition, then do this stuff.
Right.
Well, the stuff that normally in spin is indented,
Right.
underneath the if,
Right.
that's in a different scope than the if. The if is in the outer scope, and the stuff inside the then clause is the inner scope.
Inner
see.
scope.
That makes sense.
And so scope, there's multiple levels of scope.
It's like the uses of parentheses, right?
Right. And so in spin, it's all done via indentation,
Mm-hmm.
and in C, it's done with the open and closed curly braces.
Right. Which I like the
great.
indentation because like a lot of
Yeah.
the examples show indentation and they
Well,
show the
yeah.
curly brackets. So I'm like, well, choose one.
Well, the I use indentation just to make stuff look neat,
Right.
but it has to do a little bit with history, like coming from back when C was first started. There was less going on
Mm-hmm.
as far as large monitors with lots of text and all that,
Mm-hmm.
and so stuff was a little more compact,
Mm-hmm.
and so you could do a whole function like on a single line
Right.
using curly
That's what I
braces.
heard, just using the
And
little
also be
semicolons.
aware that C actually sort of predates the standardization of white space itself.
Oh.
Right.
On different text formats and different computers, they treat things like character 13, character 10, and the tab character. Back then, they would all treat those characters slightly differently.
Mm-hmm.
Right.
And you'll see problems with that still today if you're working on a file on a Unix machine and you download it onto a Windows machine. Sometimes you'll lose some of the formatting. Strange things like that. And
Yeah.
C just gets around it by using physical characters that you can
To
see.
represent it, yeah.
Right.
So that was the only thing, I took what I learned from spin and I was like, well, I'm just going to add a semicolon here because that's what is required. Like it was just a matter of adding.
Yeah. A lot of it is pretty similar concept wise. It's just learning the new syntax and what you have to type to make it compile.
Right. And then there was something about C being object-oriented programming, and to a certain
Well, C++
extent,
is.
oh,
C
not C.
isn't by itself.
I see.
Object-oriented programming is more concept than the language, but
Yeah, well, that's what I was thinking, because I mean, to a certain extent, spin could be
well, spin
construed.
is object-oriented also.
Oh, beautiful. Okay, so it is object-oriented because you use objects and you can
Right,
reference
and
objects and stuff like that.
yeah.
Yeah. So when I was told, well, someone said C was oriented, and but that didn't phase me, and I was like, aha, yeah, well, so spin. So, huzzah! I know that.
They probably were saying C++.
Yeah.
C predates the concept of object-oriented programming.
Right.
Well, the popularization of the concept. The
Sure.
concept has been around for a long time.
I see. So anyway, so for those who, are interested, who know spin or have been learning spin with me and are on, roughly the same level of noobish awesome, if you want to like learn spin, like look up those tutorials or whatever, and you actually might get it pretty easily, because the first program that I ended up doing, so I went with a tutorial for a few lines, and then afterwards I like kind of finagled with it, and now I have a like program where you put in two numbers and you can get the sum, the difference, the product, and the quotient. Yeah, that's right.
And you can do all that on a propeller now with prop GCC and
really,
and make it even easier with simple IDE.
Wait, so do you program in C for prop GCC?
Yeah, it's C or C++.
Oh ho.
So if you go get simple IDE, it'll include prop GCC, and you can write your little program that you did for C there into that and compile it onto the propeller and make it run over there instead.
Well, what about floats?
It does it. It just emulates floating point math.
Huzzah! Yeah, so I thought that was okay, cool. So you can even do it for
now. How about with the S? What is it? Is it what's the one you always include for using the console?
Standard I/O.
So is it STIO?
STD.
STDIO. Like yeah, they have a propeller implementation. In fact, they have a couple of them because they have the full or almost full one, which is somewhat large, and then they have a stripped down simple one, which doesn't include as many features but is much smaller.
Now, does that work over serial?
Yeah, so what they did is they made it so that if you try to write the standard out, it does it through the, a version of full duplex serial that writes it out to the serial port.
Pretty handy.
And standard error, I think, also does that too. And then standard in comes in from the serial port.
So then what kind of window pops up? Because when I do like that little calculator program,
you would have to run the serial terminal just like you do with prop tool, right?
I see. Okay.
So you compile your program, and then I think simple IDE actually might have a serial terminal
that pops up. Okay. Yeah.
That you can switch over to.
It's helpful to think of the command line as a terminal, right?
Yeah.
Right.
So you can pipe the inputs and outputs of a program from a terminal, right?
Sure.
And that's basically what you're doing on your little C example, is the command line there is your terminal.
Mm-hmm.
And when you move it over the prop, it's just being piped over serial to your parallax serial terminal, right?
I see.
They're essentially the same thing. It's just, back in the day, the terminal that you were working with on a computer wasn't necessarily part of the mainframe computer itself.
I see. So, yep. So, hardcore C expertise, go me. Woohoo, calculator.
Hardcore basic fundamental C that hardly does anything.
Awesome.
Now, did you get it to print out "Hello World," or did you just skip that?
I skipped that basic step because that was
went
very
to the print F with various percent things to do the %d, so you could print out the result of
right, but then
math operations.
But then I was told that, obviously if you're dividing 4 by 3, because it can't do float math with %d, then you have to use %f.
Well, yeah, but it's actually not that %d is doing the math. %d is just trying to display
it's getting
the
result, integer. Yeah.
And it casts it into an integer because, it doesn't cast it. It depends. You can actually get yourself into trouble with printf % notation because you could say %d and then pass in some other type and it will try to display it as if it were an integer and it will look really weird.
Yeah, that Whisker messed up my program just by doing that because I think the first
He's like,
question,
here, look at this shiny thing I made, and I'm like, type, enter,
was
and it goes,
put in. I think it was put in a please put in a number, and Whisker typed out 2, like TWO. And then my program like freaked out and I'm like, thanks.
No problem.
Thanks.
Yeah. See, that's one of those things where you used scanf to do your input.
Yes.
And scanf is very limited and unsafe because people can type whatever they want.
Yeah.
And it's just going to go into your buffer.
Yeah.
And so unless you're really careful, they can do all kinds of nasty things to your program.
Yeah, that's what
So it's a general rule. Most people don't use scanf.
I see. Well, it was
you see it in like school and in tutorials, and that's it.
Yeah.
Like the more normal way to do things is to actually do the input one character at a time and parse it and turn it into what you want it to be.
That's me making a face of yuck.
Well, it's just like, so you could do a simple little loop that would get one character at a time, and if it wasn't a digit, a number character, you could just ignore it and not accept it, and then just only accept numbers, and then Whisker wouldn't have been able to screw it up.
It'd been like, is that you, Whisker?
Now, that sort of thing is what causes problems like buffer overflow exploits.
Right.
I could write, if I knew how large the buffer was that it had allocated for whatever the input was, I could fill that up with crap and then keep going after. And then after, get myself into an executable part of your code there and start putting like machine code right down into that spot.
What?
And
just in my little program, you could do that?
I could completely own that computer, yeah.
Yep. That's how a lot of these hacker exploits work. Is that they feed in an input, a program takes some input, right? And they just feed in extra stuff beyond what the program expected. And it overflows some buffer and then starts smashing memory with its own values and eventually fills it up with assembly code to do something nasty on your computer and causes it to execute via...
I have a question, okay?
Throw a bunch of jumps in there all to the same address, and
wait a minute.
No matter where it lands, it's going to hit a jump that goes to the beginning of my code, and whoop, off you go.
Wait a minute. So, say I put my program up again, right? And ran it, and then you decided to put like a thesis of how dangerous scanf is, right? You just copy paste it, right? It would write my program, like would it write into the compiler? How would it manifest?
Write memory.
Actual memory on my computer.
Yeah.
Yes.
The RAM.
Where
and
that
of
program
course, there's other programs executing in memory
kidding
too.
me?
So all you have to do is land onto a point in memory where an execution pointer is going to come by eventually, and yeah.
Well,
so even my tutorial program is not safe.
So hold on.
Yeah.
The most common way that it works, and this requires that you understand a little bit about some low-level stuff, which you're not going to understand, but Whisker does, which is that your local variables, like the variables that you put right there in the program function, right where you were doing it, well, those variables are on the stack, and the stack is where it stores the return address from when your function is going to return back to the thing that called it.
Okay.
And so if the buffer which has your variable in it is too small and they overwrite past it, they could end up overwriting the return address to where you're supposed to go back to some other value.
So truly, my little calculator program, if in the wrong hands, could seriously mess my computer up. Could actually mess it up.
Well, in that program, if they were sitting at your computer, right? Because that's only taking input from the console, which is right there.
Yeah.
So if somebody knew exactly what characters to type to fill up your buffer and corrupt the stack and do something, then yeah, they could mess up your computer.
I'm so mortified right now.
but like I said, in this particular case, because that input is only coming from the keyboard, they would have to be sitting at your computer. So it's
but Whisker could
not
have
as dangerous.
Blah 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 blah, and like bam, my computer doesn't boot.
I know that's how I code. I just like sit there and say blah blah blah, and then just stuff happens. It's great.
Oh my gosh!
It takes a little bit of research. Most of the time, where this becomes dangerous is like, a commonly used program like say Internet Explorer has a bug in it somewhere where it doesn't check a buffer. And people know this and they figure out and they research that portion of the code and try to figure out what can they put in there in the exact order to make it do what they want. And then they put it on a web page somewhere. Then they put it on a web page somewhere for you to hit, and then it takes over your IE. Right? That's kind of how it works.
And this kind of thing is exactly why the first thing I typed into your program there, when you said please enter a number, I just type in the number. I knew it was going to break.
I know you knew it was going to break.
That's the exact sort of thing programmers.
Because I didn't bother. But see, that's because I don't know how to put in what's the word?
Protection.
Yes. I don't know how to put in protection
yet. But this is something that, it's important to think about this also for the propeller, because you want to check what the input values are, because you'll be setting IO pins to some value based on those inputs, and those IO pins could be controlling a motor, or they could be controlling some voltage output.
Robotic and they could damage something. Boom.
Let me ask then. So say this program, this is a similar program on the prop, right? And in the serial terminal, the person is asked to put in a couple numbers, right? And then the prop would, do a whole bunch of awesome math, arithmetic, right? So then, in the same way that putting in a thesis about the problems of the world would be to screwing up my computer, could we theoretically overwrite, like...
It's a little more difficult with the prop because of the way it works.
Okay.
But I mean, it's possible they could definitely input a value that would make it do the wrong thing. Not produce the correct result,
like
or
0
possibly, end up in a bad, situation.
But the buffer overflow situation would not.
That's still no. It could still exist. It just depends on how you'd have to. Things don't work quite the same way on the prop as far as buffers and where they go in memory and whatnot. So it's slightly safer and protected from that, but it's still possible to, on input, overwrite memory and cause the program to be changed or corrupted into something different. It's just you have to be more familiar with exactly what's going on with the whole program.
Interesting.
And know when to type what, but I mean, it's definitely possible. If you don't put in protections, you should always validate your input, is what I'm trying to say.
Yeah.
Whenever you ask for input, whether it's coming from a user typing on a keyboard, or from the serial port, or from some other external input, right? Some other hardware device giving you input, you should always validate that it's something reasonable.
Yeah.
And it's usually pretty easy to do, just verify that it's within some limited length of number of bytes, and verify that the value is within some valid range and stuff like that. It's pretty easy to do. And a lot of people just don't do it, and it's unsafe.
I guess they don't think about hackers like Whisker.
Or me.
I
think about hackers all the time.
Joe Grand.
True.
Joe Grand would have a lot of fun with a little microcontroller project that didn't have any protections on its inputs.
Yeah. You could make hardware do all kinds of fun stuff because there's lots of embedded projects that don't check things.
Oh, that's so bad.
Yeah.
I didn't realize. You could have messed up my computer, Whisker.
But I didn't. So in the context of like hobbyists messing around on a prop BOE, no big deal, right? You blow something up, it's your own thing. But you move this in a context of like designing industrial automation equipment or something like that, where you've got, 5,000-pound stuff moving up and down with people standing around it. You've got to know your stuff.
Yeah.
And you've got to protect those inputs and outputs, because the thing that can happen in a normal everyday situation like that is not necessarily somebody trying to corrupt it, but it gets dirty or a part burns out that's part of the input, and then it starts giving you garbage data, and then you start trying to respond to it, and you swing the big giant robot arm around and knock somebody over instead of picking up the part and placing it in the right place. So most of that kind of equipment has, double and triple safety checks and backup redundancy things.
No, so are there any certain safety things that you guys always put in your code regardless of what it is?
Well, usually if I have a user inputting a number, I make sure it's a number.
It's sort of like step 1, and then step 2 is like making sure that it's within the range. Because what was the second thing I typed into your program?
Negative 2E2 or something like that.
So if you do
which it totally handled.
It did, but if you did like a negative 2E6000 or something like that, that's a really, really big number.
You could have messed up my computer.
Well, I could, overflow that variable, right?
Yeah.
Right.
And either it's going to handle it gracefully or it's not. Probably not.
Oh man, that'd be so bad.
So you can check that before you pass it on to the next thing that's actually doing something with it. You can check it to make sure that it's within an acceptable range. For example, if you're going to be putting that information into a single byte, you're going to want to check to make sure it's between 0 and 255.
Right. And when you have floating point numbers, there's other things to factor in, like if you were to put in 2E6000, that's an invalid number. Right, it's 6,000 exponent is too large and it wouldn't fit. There are other invalid values for floating point that have special meaning. Things like not a number and infinity. And once a floating point number has that value, it causes things to act weird as far as comparisons and whatnot. Because comparison not a number equals always false and stuff like that. There's other things that can mess you up when you start dealing with floating point numbers beyond
integers for everybody.
But I mean, it's all useful stuff. It's just, again, just to reiterate on the double check your inputs when, to make sure they're what you expect before you actually try to use them.
I'm trying to think of, like, say, the modules that we've used and whether or not.
A good example would be when you thought you were working with your altimeter module and you actually had your compass module plugged in.
I'm not supposed to tell people.
See, if you had code to check the input values, you would have known that it was giving you bad input values.
Well,
and then you might...
I mean, I saw the values and I saw that they were bouncing.
No, but I mean, I'm talking about at the lowest level, like right at the raw inputs. You would have found that you were always getting 0, and that would have been like, hey, that doesn't make sense.
Oh, I see.
And you could have looked at the module and went, oh, I got the wrong module plugged in, and swapped it out before anyone noticed, and then you would have seen you were much better,
And then I wouldn't be so embarrassed.
Exactly.
Okay, so we just have a couple minutes left here, and I believe you said you wanted to update everybody on the quest for Sigma Delta.
Well, I didn't think that talking about my C experience would cause us to go into, like, illegal hackery, but Yeah, so Delta Sigma, I had the opportunity this past week to look a little bit more into it and what it's about. And essentially it's a type of modulation, much like pulse width modulation, that uses a lot of, I guess, analog trickery, to make analog go into digital for, say, ADCs, or for digital to go into analog. And um, the digital that goes into analog is kind of like how it works when we were talking about sound generation,
right,
and pulse width modulation, and the use of low pass filters. So for delta sigma or sigma delta, same thing, give or take. There's always this bit stream, kind of like that 1 0 1 0 1 0 for the pulse width modulation, and it uses actually what is known as pulse proportioned modulation, PPM.
Okay.
And that actually is kind of like how servos run. So
Right.
servos are like, we had the whole debate about servo pulse width modulation versus duty cycle pulse width modulation and all that.
Right.
Servo
Right.
pulse width modulation is actually technically known as pulse proportion modulation. So the
Right.
proportion of pulse is what determines what happens, right?
Yeah.
So same thing with these sigma delta ADCs. And so there's the bit stream with the ones and the zeros, and then after there is a filter, a low pass filter. Now this low pass
So you mean
filter,
DAC, not ADC.
both actually. So if it's an ADC that you're working with, that low pass filter is a digital filter. And if you're working with a DAC, then you're working with an analog filter, and you're doing that smoothing biz. So
right. So
the structure is
when
the
you're
same.
when you're doing DAC, your low pass filter is on the pin doing, it's a resistor capacitor thing that's filtering the digital input into an analog signal.
Correct.
Whereas when you're doing the analog to digital, that filter is actually taking the analog signal and turning it into digital through some mechanism with the counter pulses and the feedback, right? Is that kind of what you're saying?
Kind of what I'm saying. It's like a 1-bit DAC,
Right.
I think is what they call it.
So
Wait, something like that.
I just wanted to mention, because you haven't yet, that you did post a little bit about this on your Tumblr.
Yes.
And we'll include links.
Yes.
And it's go into a little bit detail on this so that people can go read that before the next show or the show after when we actually discuss this.
Right. And the posts are pretty meaty, because sigma delta modulation is actually a pretty, I think, complex
non-vegetarian topic.
Correct.
Yeah, it is pretty complicated.
Yeah. So
you have to understand a fair bit about the analog hardware side of it a little bit too.
Yeah, just a bit. So part of this is if we're talking about sigma delta modulation in general, my posts talk about the difference between normal pulse width modulation modulators and sigma delta modulators. And the reason that most people, well, not most, but people end up using sigma delta is because it's a faster form of encoding. So you can get your signal a lot faster than just by using typical pulse width modulation. Okay. And that's because of how the counters work in the system, and because of how they're incremented. So without going into all the details, pulse width modulation, the counters go up by 1 each clock cycle, whereas the delta sigma counters go up by the amount that is proportionate to the input. So if the input is like 50% duty cycle, right? Which is like what, 128?
It depends. I mean,
all right, let's assume 128 out of 256, right? Then the counter goes up by 128 in that same amount of time. Do you see what I mean? So instead of 1, it's by 128. So you go through the signal, you get these signals so much faster, and the modulation gets through so much faster. So
right.
And then if we're talking on propeller itself, so I looked through the app note a little bit, and to me it's still kind of complex. But what it seems to be is that there are these, like, ideally you need to have the surface mount propeller chip. I think the QFN, is that correct?
Right, and like the quick start has this built in. It has the pads built in right next to a couple of the pins to actually do a sigma delta setup.
Right, and so then it's like
you need to put the parts right next to the pins.
Right,
because pins and traces have capacitance.
Right, so it's a matter of, I think, like having a resistor, a couple of capacitors, another resistor, and then I think those connect to the counter.
Two different pins.
counters. Yeah. So
it's two different pins on the same counter, one of them being a feedback pin and one of them being the output.
Right. So anyway, I mean, like, I've dived into it a little bit. It's a little more complex than what I think we can necessarily discuss at this point in time, because all the code that would be used to run it is in PASM. So I don't understand it, but you are more than welcome to read what I've written so far, and if it's still something that you guys are interested in, then we can certainly look more into it.
And you can also look at the app note number 8 at parallaxsemiconductor.com. It has
so it's not much more detail than what we said last week, but it but at least there's a few more resources for you guys to take a look at.
Yeah, some articles there that Addie wrote and an app note, and yeah, if you want to know more, let us know, and
I'll keep slogging away at it.
Yeah. All right. Well, that's all the time we have for this week.
Boo.
You can find the show every Tuesday evening at firstspin.tv. There's an RSS feed link on the side. You can automatically download us to your phone, your iTunes, or just press play on the page. It's really easy, and it's really fun to make Roy fit inside your phone and carry him around.
That's true. You have a little Roy.
All right, that's it for us for this week. We'll see you guys next week. Bye.
Bye.
See ya.